Thank you, Tony, and thank you again, everybody, for being here, of course. We have two talks today. The first one is from Lina Sjur, and the second one from University of Oslo, sorry, and the second one from Spall from Oceanographic Institution. And we are going to talk about ocean dynamics and circulation, essentially, around the large-scale basins and the exchanges between the marginal seas and the open ocean in the second talk. Lina is going first, if I remember right. So if you want to share your slide, the floor is yours.
Thank you. And thank you for the introduction. Let me just hide the toolbar here. Okay, so for the last couple of years, I've been doing a PhD at the University of Oslo, Norway, where I've been studying the large-scale flow in the Arctic Ocean and the Nordic seas. And the main aim of has been to take the very complicated equations describing this flow and try to break them down into their most important components. And by doing that, getting an intuitive understanding of what's driving this flow. So let's start with an overview of the region. So to the left here, you see the Nordic seas, and the arrows indicate the main pathway of the currents transporting warm Atlantic water into the Arctic Ocean. To the right here, you see the Arctic Ocean, and the yellow arrows indicate the surface flow, while the red arrows indicate the subsurface flow. So what I want you to notice from these figures here is that flow tends to travel around basins following the continental slope and underwater ridge systems. Another way to put this is that we have very strong topographic steering in the Arctic. And it is thus meaningful to talk about the circulation around depth contours or around the basins. And when I say circulation, I mean the integrated velocity around close depth contours. So it's kind of like a mean velocity. And we are not talking about the connection with other basins here at lower latitudes. So we're kind of limiting our review here to circulation within the basins. So to say something about what's driving the circulation, we look at the momentum budget for a depth contour. So to arrive at this momentum budget, we start with the full momentum equations, which are basically Newton's second law. And then we integrate them through the water depths and around a closed contour. So then you get something like the figure that I have here. So the gray lines are the topographic contours. And then you see a depression in the middle here, that could be a basin. And then you can imagine the contour as a curtain extending from the seafloor up to the seafloor surface, forming a closed loop. And here, this equation that I have here is our momentum budget for this contour. And it's simplified. We have not included any of the nonlinear terms here. So this is a linear idealized model. And what this tells us is that the change in circulation, this first term here, is given by an imbalance between two terms. So the first one here, that's the integrated surface stress around the contour. And the second one here, that's the bottom friction, or represents the bottom friction. So what this tells us is that if you have wind blowing at the sea surface or ice drifts, the circulation will speed up until the friction is strong enough to balance the stress at the surface. And this idealized linear model has been applied to the Arctic before. In 2003 in a paper by Saxon et al. And they found very good quite good agreement with observations for the Nordic seas. They also compared it to a numerical simulation of the Arctic Ocean and found also quite good agreement. However, this was back in 2003, so numerical simulations were quite coarse. And now we have much more high resolution simulations which contain a lot more non-linearities. So we wanted to see if this very simple linear idealized model is still useful. So we considered a numerical simulation called Arctic 4, which is a coupled ocean sea ice model, which has a 4-kilometer resolution, so it's quite high resolution. And to the right here, you see the model domain. And I have marked 4 of the depth contours that we applied our idealized model to. So let's have a look at the results. So what are we seeing here? The blue lines, that's time series of the circulation in Arctic 4. So this is from a numerical simulation, very high resolution, running on a supercomputer, producing terabytes of data, and it's also quite demanding to analyze, while the orange lines are one-line equation, and they agree quite well, actually, especially in the Nordic seas. At the bottom here, you see that they agree very well. This is a region where we have mostly positive circulation, so cyclonic circulation or anti-clockwise motion, while and we also see that we have quite good agreement in the Arctic Ocean, the top 2 here. The agreement is maybe a bit worse when we have strong anticyclonic or negative circulation, but still quite good agreement. But even though that we have quite good agreement, there are some systematic differences between these 2 lines. It becomes even more clear when we analyze even more contours within each basin and plot it as a scatter plot, as I have done here. So if we would have a perfect match, the data would fall along this 1-to-1 line. And it does fall quite close to that, indicating again this very good agreement. However, the data seems to fall a bit closer to a line that's slightly shifted upwards from the 1-to-1 line. So this tells us that the circulation in Arctic 4 is slightly more cyclonic than in our linear estimates. Another way to put this is that our linear idealized model is missing some dynamics, giving slightly more cyclonic values. This is consistent with theories of deforced circulation in basins. Some of you might know this as the Neptune effect. Okay, so this was all for numerical simulations. We actually got a chance to look a bit deeper into this in observations, and specifically in a region in the Norwegian basin, which has a lot of eddy activity, namely the Lofoten basin. So we had Sean Johnson from Scripps visiting us, working with Argo floats. So an Argo float is a autonomous device drifting with the ocean currents. And at regular intervals, it's ascend to the surface, measuring temperature and salinity and transmitting data via satellite. And this gives us valuable information and observations from regions which are otherwise very hard to observe. So Sean Johnson did an amazing job at collecting Argo data for this region here that you see marked on the map. That's west of the Norwegian coast. And he created maps of velocity, like the one you see here. So the black lines show the velocity. You can also see the temperature in this plot here, so you can see that we have higher temperature in the Lofoten basin. This plot next to that is the RMS velocity. So this is a measure of eddy activity. So you can see that we have a lot of eddy activity in the Lofoten basin here. And from this velocity data, we could calculate circulation around a depth contour in the Lofoten basin. And that is what you see in red in this figure down here. We could also calculate our linear estimates based on our idealized model from wind data, and that is what you see in blue here. So you can see that the 2 lines, they correlate quite well. They have similar variations, but again, we see this offset, that we have a bit stronger cyclonic circulations in the observations than estimated by our idealized model. So again, we see this shift, which we think were due to non-linearities. So let's go back to our momentum budget. and our idealized model, and also includes the nonlinear terms. And what we then get is this extra term here at the end, which looks like a flux of vorticity in and out of the contour. And what this term here tells us is that if we have an eddy with positive vorticity, so positive rotation going into the contour, or an eddy with negative vorticity going out of the contour, you get an increased circulation. Sadly, our observations from the Lofoten Basin did not have high enough resolution to actually calculate these fluxes. So instead, we went to a very high resolution model that we have of the Lofoten Basin, the Lofoten 800 model. And what you're seeing here is a snapshot of the vorticity field in that model, so you can really see a lot of eddies in this region here. Okay, so then we could calculate the circulation in the model around the depth contour in the Lofoten Basin. And this is what we got. So in red here, you see kind of the true model circulation. And then the blue line shows the linear estimates, which take into account only the surface stress. And you can really see that they're underestimating the circulation. However, if we also include vorticity fluxes, so that's the full equation down here, we get the darker red line here. And even though it's not perfect compared to the true circulation, it's still a lot better than just considering the surface stress. And we can really see that by including vorticity fluxes, we get a lot stronger circulation matching what we see in the model. Finally, I also want to say something about the need for high resolution. So here I plotted time series for the same contour in the Lofoten Basin, but one from the lower resolution model that I talked about in the beginning, Arctic 4, and then also for Lofoten 800. So you can see that the wind-driven estimates are actually quite similar in the two models. That's the blue lines. If we then look at Arctic 4 and the darker red line where we include vorticity fluxes, you see that they do increase slightly and also match quite well with the true model circulation. While when we have higher resolution, we really get an increase in circulation, showing that vorticity fluxes really contribute to the circulation here. So to end with, I have some takeaway for you. So we see that surface stress can explain a lot of the time variability of the large-scale flow. So if you want to see how the circulation is changing, you can look at how the surface stress is changing. However, we have this cyclonic offset. If you also include vorticity fluxes, we do get an increased cyclonic circulation. And I think this is interesting because we are used to thinking about eddies as transporting tracers, like heat or salinity into basins. This shows that they are also transporting vorticity affecting the circulation. And finally, we see that we need very high resolutions to resolve these vorticity fluxes, and that's both in numerical models and in observations. So here's some references, and thank you so much for your attention.
Thank you very much, Lina, for this great talk. It was very interesting. I would suggest we can move on with Mike's talks, and then we have questions at the end of the two talks, if that's okay. Mike, if you want to share your slides. And I think you're still muted.
This happened before. Let me see here. Sorry about this. I thought we had this sorted out before.
No worries. And while Mike is pulling that up, we do have a question in the chat from Mary Louise. Lina, I don't know if you're already
Okay.
looking at that or typing away, but it's a clarification about including sea ice in your surface stresses.
Yes, so I'm taking the surface stress that the model is, the numerical model is feeling. So that includes the effect of ice. Yes.
And Mike, let me know. I do have your slides as well, if that would be easier.
Yeah, I brought my slide up and now I can't see the share screen. And if I bring it up otherwise, it didn't seem to go back.
Yeah, the share screen option might have disappeared behind the 3 ellipses under more on the Zoom toolbar.
Sure, why don't you just bring up the one I sent to you?
Sure. Okay, let me.
Okay,
Okay.
sorry about that.
No worries.
No worries.
So this is actually closely related to Anna's talk, at least in the central part of the talk. So I'm interested in the variability of exchange between marginal seas in general and the open ocean. I don't think I need to go too much into what marginal seas are, but they're, I think, places to look at seasonal variability because they're generally surrounded by continental land masses, and we can expect strong variability in both wind and buoyancy forcing on seasonal timescales. There's been a lot of work done on the buoyancy forcing aspect motivated by the Labrador Sea, the Greenland Sea, and Mediterranean Sea. So I'm going to focus more on the wind forcing. Marginal seas are important because water masses produced in those marginal seas are often found quite far from the source, and they transport heat and salt and mass long distances from where they're formed, even though their spatial area is relatively small. So this project was motivated by the Nordic seas and the overflows at Denmark Strait and Fairbank Channel. But my approach, as you'll see, is very general, so I think it will remain relevant for other marginal seas as well. Next slide, please. Okay, so we're familiar with the general circulation in the Nordic seas. We just heard about that. There's a couple of warm inflowing branches. There's 3 really. One comes in through Denmark Strait, and then 2 larger ones come in through Fairbank Channel. And water mass gets transformed both in the Nordic seas and in the Arctic, and you get an outflowing of salty cold water and cold fresh water near the surface. So the middle panel is a time series of the Denmark Strait inflow. You can see there's interannual variability. This is a span of 20 years or something. There's some interannual variability, and you can see a strong seasonal variability, this higher frequency. If you average this into a seasonal cycle, there's weaker inflow in winter and stronger inflow in summer. If we look at the Fairbank Channel overflows, so there's a dense water coming south, you see similar magnitude interannual variability and also a seasonal cycle. And there is a weaker outflow, the sense of the sign change. So there's weaker outflow in the winter, stronger outflow in the summer. Denmark Strait, the overflow shows very little, a very weak seasonal cycle. So wind forcing, buoyancy forcing are both stronger in the winter, but the exchanges are stronger in the summer. This is from another publication from Lyons, and you see the same kind of Fairbank Channel overflow seasonal cycle. And this orange line is essentially a measure of the cyclonic circulation, the anticyclonic circulation in the Norwegian Sea. I'm not going to talk too much about that, although it is relevant. Next slide, please. Okay, so we just heard about circulations within closed topographic contours. So for the Nordic seas, that's about 850 meters depth. That's the sill depth in the Farabank Channel. That contour is outlined here. So I'm going to treat the interior dynamics differently from the dynamics on these contours that do not close within the Nordic seas. So first, in the interior, if I integrate the Ekman pumping within that 850 meter contour, I get this time series over 20 years. There's interannual variability, there's synoptic variability, which are these really spiky events, and there's seasonal variability. So I'm going to focus on the seasonal. We average this into a seasonal cycle, get a maximum cyclonic wind stress curl in the winter. It's about 2 spheredrips of upwelling, and it's very nearly 0 in the summer. So this simple periodic forcing is what I'm going to consider. We just heard about circulation governed by the integral of momentum equation from these older papers. And I'm going to build on that, although look at it in a slightly different way. Next slide, please. Okay, so most of what I'm going to talk about has to do with the exchange through the straits. But before I do that, I want to spend a very brief summary of what's going on in the interior. So if we consider a very idealized marginal sea, circular topography, periodic uniform wind stress curl in the interior, we can solve those integrated momentum equations, again, the linear form. You can get an expression for the along topography velocity. This is the wind magnitude. It's linear in radius. It's periodic in time. There's a phase shift. It's inversely proportional to the bottom drag. And then there's this alpha parameter, which turns out to be important. Alpha is the product of the forcing frequency and the spin down time scale. I'm more interested right now in this cross topography velocity. It's proportional to the Ekman transport, which is this term here, scaled by this alpha over 1 plus alpha squared. So if alpha is small, the cross topography transport in the interior of the water column, so above the bottom Ekman layer, is very small. That's at low frequency, right? Omega small. At high frequency, essentially all the Ekman transport's carried in the interior of the water column, and there's very little carried in the bottom Ekman layer. Next slide, please. So that basic relationship I can test here with an idealized version of the MIT GCM. I'm not going to go into any details really, but I've varied the bottom drag coefficient. I've varied some other parameters, Coriolis parameter and things like that. And I'm plotting the diagnosed radial transport in the interior, psi sub I, scaled by the Ekman transport. And each of these symbols represents a model calculation. And this solid line is that theory that I just showed you. So there's pretty reasonable agreement. In order to calculate alpha, I have to choose a depth. But of course, this transports over a range of depths. So I just picked one fixed depth and used it for all of them. We see the same behavior that we were predicting. So at low frequencies, the bottom Ekman layer does all the transport. At high frequencies, the interior of the water column does all the transport. And if I put in typical parameters for the Nordic seas, alpha is order 1, it's 0.4. So we can expect on seasonal timescales that the transport, there's a barotropic radial transport in the interior, and there's also transport in the bottom Ekman layer. All right, next slide. Now I want to consider the open contours. I'm going to start with a really simple conceptual model of the shelf. So imagine here's a piece of the shelf, here's a boundary, here's a strait. I'm going to say that the wind is blowing parallel to the boundary. That gives us some offshore Ekman transport. There's going to be some along shelf flow. And associated with this along shelf flow, there's a bottom Ekman transport onto the shelf. I'm going to assume that the pressure on the boundary is 0 here at the strait. That's equivalent to saying there's no variability forced from outside the marginal sea. I'm considering only variability forced from the winds within the marginal sea. So we can write down the mass budget for the shelf. The divergence of the long shelf velocity is just the difference between the surface Ekman transport offshore and the bottom Ekman transport onshore. Next slide. So there's a simple solution for that equation, and I take a pressure anomaly as 0 at y equals 0. This is the along shelf velocity. It's proportional to the wind. It's in phase with the wind. It's inversely proportional to the bottom drag, and it has this exponential behavior. So y equals 0, there's no velocity along the shelf, consistent with me saying that the pressure anomaly is 0 at the strait. But as we move cyclonically around the basin, this term gets smaller and we develop an along shelf flow. It develops on this length scale, which you can interpret as the distance a shelf wave would propagate over the damping time scale. So F times L is roughly the shelf wave speed, and H over CD is the damping time scale. Now I've ignored that interior transport because on the shelf, H is very small and that transport is unimportant, and most of the transport's in the bottom Ekman layer. So if the basin is small compared to this length scale, then most of the Ekman transport into the basin comes from outside the marginal sea. It's all coming from along the shelf. But if the basin's really large, then the shelf has a chance to spin up to this equilibrium velocity, and then most of the Ekman transport into and out of the interior of the marginal sea is coming from upwelling or downwelling along the boundaries. So those are two very different scenarios. One's coming through the strait, the other one's coming from within the marginal sea. Next slide, please. So if you forget everything I said today, but one thing, this thing in the box is the thing to remember. So if the flow along the shelf is coming from outside the marginal sea through the strait, let's say that's all that was going on in the strait. You're just exchanging water in and out. If we had a flow of about 1 Sverdrup, it's on the order of the Ekman pumping, that would cause a, depending on the size of the marginal sea, between 1 and 10 meter change in the sea level in 1 year. Well, we don't see that. And the reason is that the sea surface is so rigid that it develops quickly a barotropic pressure gradient that closes the mass budget in the marginal sea. So the water that's coming in and out on the shelf is quickly balanced by water coming in and out in the deep part of the strait. Right? So this is a direct connection between what's going on the shelf and what's going on in the deep part of the strait. They're connected through the mass budget. Next slide. Okay, now I'm going to do some idealized numerical modeling. This is my model domain. I've got circular bottom topography in the interior. There's a little strait here. This is the boundary of the marginal sea, this white. And then this funny skinny blue region out here. I damp the velocity to 0 and the tracers back to the initial stratification. So that prohibits variability that might be coming in and out of the strait from propagating around the basin and coming back in over here. So this is my way of imposing the pressure anomaly is 0 at this inflowing corner of the strait, inflowing in a shelf wave sense. Enforcing with a periodic Ekman pumping on the order of Sverdrup, so that's about Nordic seas like. Now, if I calculate the integral of the transport as across the strait as a function of time and depth, this is one period of forcing, 1 year, and this is depth. We see in the first half of the year, when there's upwelling in the marginal sea and cyclonic wind stress curl, the upper ocean is flowing out of the marginal sea, and the deep is flowing into the marginal sea. So at any time, the mass flux, net mass flux through the strait is nearly 0. So the mass budget is closed in the marginal sea. If we looked in more detail, you'd see that this outflow was happening over here, shallow by the shelf, and this inflow is happening down here in the deep part of the strait. So they're really barotropic exchanges, even though in this presentation it looks baroclinic. The magnitude of the exchange is about 1/2 a Sverdrup, which is 60% of the Ekman transport. So for these parameters, this is telling us that a significant part of the Ekman transport into and out of the interior is coming through the strait, and there's a compensating deep flux. Next slide. Okay, there's lots of intermediate steps. I'm just going to jump right to the end. I can run the model varying all these parameters that my theory says should be important, the shelf depth, the shelf width, the bottom drag, the Coriolis parameter, and diagnose the magnitude of the flux through the strait. I'm scaling it now with the Ekman transport. So, and then plotting each calculation as a dot on this set of results. So if they fell along this line, it would be a perfect agreement between the theory and the model. Most of them are reasonably close. There's a little cluster down here that the model predicts more transport than the theory. The common theme through all of those is that the shelf is very viscous. It's either very shallow or very narrow, or the friction is really large. But barring that really viscous limit, I think there's pretty reasonable agreement. And again, this is telling us that there's a connection between the shelf dynamics and the deep strait dynamics. Next slide. Okay, so this is motivated by Denmark Strait and Fairbank Channel. So far, I've only talked about one strait. Now I have two straits. The same basic setup for the marginal sea, but now I've got a shallower strait over here to the west and a little deeper strait over here to the east. So this is sort of Denmark Strait. This is sort of Fairbank Channel, and this little bit here is Iceland. So the same diagnostic. Now we see the western strait. There's a large outflow of water along the shelf in the winter and a large inflow in the summer. Fairly weak exchange down here in the deep part of Denmark Strait. In the eastern strait, Fairbank Channel, there's a very weak seasonal cycle in the upper ocean, but there's very strong seasonal cycle in the deep ocean. And the phase of this and the amplitudes of this are broadly consistent with what we see in the observations. The Denmark Strait inflow is weak in winter. That's because the anomaly is going to the south. Now I'm only talking about anomalies. I have no mean wind stress curl. But if I add a mean cyclonic wind stress curl consistent with the observations, the anomalies are essentially the same. So we can just look at these as perturbations to the mean exchange, and everything kind of carries over. So this outflow is consistent with that weaker inflow. This enhanced northward flow is consistent with that. The magnitudes are about right. These aren't spheredrups, these are meters squared per second. But if you put them into spheredrups, you get the magnitude about right. And we see most of the deep exchange is here in the Fairbank Channel, and there's very little seasonal cycle in Denmark Strait. And most of the inflow is happening over here because this has got a very long boundary upstream in the shelf wave sense. This has only got a very short boundary. So relative to the length scale, that damping length scale, this one is long and this one's short. So we get all the inflow in the upper ocean here. The deep flow chooses the Fairbank Channel simply because it's deeper. If I make these two the same depth, then we see most of the deep exchange over here. Next slide. Okay, that's the story. The Ekman transport into the interior is provided by a combination of the long shelf flow and local overturning within the basin, and that depends on this non-dimensional parameter that's the product of the frequency and the damping time scale. So from small marginal seas or for really fast waves, most of the Ekman transport comes in and out through the strait, but that's not all because that causes a deep in and out flow to balance. So the big picture message is that the dynamics on the shelf are connected to the overflow dynamics driven by wind. And finally, the idealized model is broadly consistent with the predictions from the theory. Now, the theory is making a lot of assumptions. I have a flat, uniform width shelf. I have linear, spatially uniform bottom friction, simple winds, everything's simplified. So while conceptually it's attractive, it makes it difficult to make a direct comparison with the real world because the real world's messy. And, you know, we've got variability coming from outside. We've got variability in the topography, variability in the winds. Everything's much more messier. So I think of this as kind of a useful interpretive tool, providing a mechanism in a fairly simple, clear way. I think there's still some work to be done to test this in a more realistic configuration. So that's it.
Thank you, Mike. Thank you for this talk. And I think we will leave it the rest of the time. We have about almost 20 minutes for questions. I see there were a couple of questions already for Annalena in the chat from Wei Chang and from Wilbert. Wei, do you want to actually ask the question?
Yeah, I can start, but Mary Louise also has a question. Anyway, yeah.
Oh.
Yes.
Oh, mine got answered. Thanks.
Oh, okay. All right. Yes, so you show two examples, right? I noticed the 4 kilometer resolution and then this very high res, 800 meters. That's also a numerical simulation, right? I noticed the blue line, which is so-called wind-driven component, that went down quite a bit. I wonder whether it's because some of this internal rebalancing or balancing terms are working differently in this setup, or whether your wind forcing product has been different between those two cases. So
yeah. Good question. So the two models cover different time periods. So the wind forcing is slightly different between the two periods. So that's part of the answer, I think. Also, the friction is different between the two models. So we have a bit higher friction parameter for Lofoten 800, which also dampens the effect of the wind more. So that's also why it's lower for the Lofoten 800 model. Yeah, I think as far as I can think of, that's the two reasons why it's lower in that model.
okay, thank you.
Was that question from Wilbur too?
Yeah, very nice, Annalena. Really appreciated your presentation. So as I said in the chat, it reminded me of some work I did on topographically trapped barotropic modes in the Southern Ocean. And in those cases, there is a very clear sea surface height expression of this circulation around close corners of topography. Is there something that you looked at, and did you find similar kind of hotspots of sea surface height variability that is somehow linked with the circulation that you find?
Thank you. So I haven't looked specifically at the sea surface height, but for example, in the paper from 2003 by Isaac Snetval, they do look at sea surface anomalies, and they do see a very clear signal that you can really see the topographic contours in that sea surface height signal there. Yeah, I want to check out the paper that you are writing about.
Thank you.
Thank you. Are there any other question for Annalena or for Mike?
Yes.
Go ahead.
Yeah, I could ask one, Mike. Thanks very much for the talk. You were focusing on the Nordic seas. I mean, any thoughts on the Bering Strait and, Chukchi Shelf, so on and so forth? It's one channel, and the parameters, I don't know, put it in your scaling factor. Is it a bigger shelf or small shelf? I mean, just a general, this is
Sure. We want to follow the shelf break. So to the east, you got the Canadian Arctic archipelago. So there's lots of little pieces there, right? So those are all very short pieces. But if we look kind of in the upstream, in the wave sense direction from Bering Strait, got a long coastline, right? So that would be a very large, I anticipate a very large basin and a very wide shelf. So I think you would see anomalies perturbing the Bering Strait transport from winds within the Arctic, but I think it would be less important than the local winds right around Bering Strait. Right, so there's a relationship between the winds, the northward winds in Bering Strait, local winds, and the transport through Bering Strait, because that's driven largely by the sea surface height gradient. So I think that will be more important than the remote winds. It's my expectation.
Thank you.
Wilbert, do you have another question?
Yes, this one is for Mike. So making this bridging the gap between your conceptual model and comprehensive general circulation models, kind of without kind of doing this stepwise and adding complexity step by step, what would be the best way, in your opinion, to test your hypothesis in comprehensive models? And of course, you showed the phasing of these outflows, which probably would be something that we could look at. But are there any other metrics or diagnostics that we should be looking at?
Yeah, I think there's a couple. So the theory is kind of built on the idea that you have a pressure anomaly on the boundary, sea surface height anomaly on the boundary, that's forced by winds parallel to the boundary, setting up shelf waves. So, coastal people have diagnosed shelf waves and their propagation speeds and things like that. So that, I don't know if that's doable in the Arctic because of sea ice complications and things like that. But in principle, you'd like to be able to identify shelf waves and a sea surface height anomaly along the shelf. Another assumption that I've made that I didn't talk about is that the pressure anomaly on the offshore side of the shelf is 0. So I'm assuming that the width of the shelf current is confined to the shelf, that there's nothing kind of bleeding off into the interior. That's mostly true in my numerical calculations, although not exactly true. So if you had a really narrow shelf, that assumption would probably break down. But if you had a wide shelf, that assumption's probably going to be pretty good. That would be sort of a consistency test, right? To see if that pressure along the shelf break really is constant or not. It may be hard to do because there's all kinds of other forcings going on in the model that are going to perturb all these pressure signals. So I'm not sure if you could unravel all the sources of variability and highlight one, but maybe if you did some averaging onto seasonal timescales, you could dampen down some of that other noise. The dynamics in the model are really simple. So to my eye, I'd have to come up with a good reason why they wouldn't be active. It's geostrophy and shelf waves and mass conservation. That's about it.
Great, thanks, Mike.
Question from Alaric and then Tarun.
Yeah, hi. This is a question for Mike. Thanks, Mike. It's a nice talk. I've seen it before, more or less, but I mean, it's still mysterious. So, but it's interesting. I was just wondering, Mike, if you
mysterious.
That's good. I was just wondering, could you speculate on now you focus on the seasonal cycle, and that's the big signal that you see in the in the straits. But could you speculate a bit on if you move to faster timescales and longer timescales, what kind of dynamics and how far would this model with the dynamics that you have there last in both directions? Shorter and longer, and what dynamics would kick in? I mean, it's kind of a big question, but
yeah. So there's two models that I talked about. There's the interior one, which of course built on your work, and then there's the shelf one. So on faster time scales, one of the big assumptions I make, I'm ignoring nonlinearities, and I'm assuming it's barotropic. On faster time scales, I think both of those assumptions would be good. There is a limit of the shelf model on very fast time scales. My mass budget is assumed to be closed all the time, right? And time it takes a shelf wave to propagate around that basin is about a week. So on time scales shorter than a week, the mass budget won't be closed. So things will break down at some high frequency limit. At lower frequencies, then baroclinicity becomes important and eddy fluxes probably become important, both across the shelf break and also in the interior, right? So the kind of things that you were diagnosing where the Reynolds stress terms or the relative vorticity flux became important, they would enter the equation. There's another time scale, the time it takes a baroclinic Rossby wave to propagate across the closed F over H contours. in the Nordic seas, in the Arctic, that's a really long time, right? So we probably don't need to worry about it too much there. But at lower latitudes, you could in principle apply this to any marginal seas. At lower latitudes, they can become important even on seasonal timescales. So then my model will fail.
Mhm. Yeah, no, great. Thanks, Mike.
Aaron?
Hi, I have a question for Anna. Thank you for your talk. I noticed that in your 800-meter results, there was still quite a lot of variability in your circulation, which was missing even when you included the vorticity term. Can you speculate what could those missing term could be? That's one question. And then the second one is, I also noticed that you also had some sort of a spread around your the predictions. How did you get the spread? So those are the two questions that I have.
Yes, I can maybe start with the last one, where the spread is from. So we parameterize the bottom friction as a linear friction, which is not actually the case in the numerical simulations. So we had to estimate or pick a linear friction parameter. And that we based on what fitted with the actual friction in the model. And then we got a range of friction parameters. So that's where the range is from.
Okay.
And then, so as we said, there's still not like a perfect match between two curves. So we do still do a lot of simplifications in our idealized model. For example, we assume a constant Coriolis parameter. I think that's quite reasonable. But also we assume no vertical velocities. I think that's also a source of error. I think another source of errors is that it's actually quite hard to evaluate these different terms in numerical models since it's on a C grid. You're doing lots of derivatives, integrations, and so you pick up a lot of errors there as well. So I think it's both like from physical processes and also just that it's difficult to deal with numerical simulations. Yeah.
Fair enough. Thanks.
Thank you.
Thank you. Anybody with other questions? Otherwise, Tony, we have 5 more minutes. There was something you wanted to mention?
Yeah, if there's no more questions, I don't think we have any major updates at the moment. Just ask everybody to stay tuned for information on our next meeting. We might take a little pause in December, but if so, we'll be back in January. So don't go too far, but enjoy the holidays. I guess I'll pause here since we do have a couple minutes, just if anybody in the attendee group here has any announcement they'd like to make, just any like community updates that they'd like to share with fellow members of the physical oceanography community of practice. And if not, we can give everybody a couple minutes back.
Thank you, Tony. I think if we are nothing, thank you again to the speakers. Thank you, Lina, and thank you, Mike. It was great talks and great discussions after that. And we're looking forward to see you all in a couple of months, as Tony said. So thank you again for being here, for joining us.
Yeah.
Have a good
Thanks, everyone.
afternoon or evening,
everybody.
depending where you are. Bye.
Bye-bye.